In this lecture, we are going to discuss an important aspect of friction that is known as tipping versus slipping. Before moving on to this topic, let's see one schematic here in which a block of weight W has been shown, and this block is acted by an external force whose magnitude is B in the positive X direction. So if we want to draw the complete free body diagram of this block, the normal reaction is shown here. And to oppose this force, there will be a friction force in the opposite direction. Okay. So we have shown the normal reaction here. You can see that this is actually the line of action of the weight, and in the same line but in the opposite direction we have shown the normal direction. Okay, you can see that this is the line of action of the weight, and in the same line we have shown the normal reaction, but it is opposite to the line of application of the weight. Okay, now how we say that this is passing through the center of gravity? Okay, how we say that this is passing through the center of gravity? So in actual, what we assume that the normal reaction at different points of the contact between the block and the ground is same. See, the block has so many points. Okay, the lower surface of the block has so many points, and each point is in contact with the ground. Okay, this is what we assume, that each point of the block will be in contact with the ground, and each point of the block in contact with the ground will be acted upon by a normal reaction. Okay, the ground will exert a normal reaction on each point of the contact between the block and the ground, and we assume that this value of the normal reaction is same throughout. Okay, so at different points, okay, there will be so many points of contact between the ground and the block. At each point there will be a normal reaction, and we assume that this normal reaction is same. And if we assume that this normal reaction is same, we get a kind of a uniformly distributed load. Okay, the resultant of which can be converted into a single force, and hence we show that this is the normal reaction, and its point of application will lie on the centroid. Okay, if this is the weight W, the normal reaction will be at the centroid of this loading, and obviously it will pass through the center of gravity. Okay, this is the center of gravity, and this is the weight force. This is what we assume while we are showing the normal reaction on a block. Okay, but see here, what is the actual condition of the contact between the block and the ground? If we see the microscopic view, okay, this is actually the contact surface between the block and the ground. We can see so many surface irregularities. All the points are not in contact with the ground. Okay, all the points of the block are not in contact with the ground. And also it has been seen that the normal reactions at different points of contact are different. See here, this is one point of contact. The normal reaction has been shown by, and this is delta n. Okay, delta n1, this is the normal reaction on this point of contact. And similarly, the friction force will be different. Okay, that has been shown with delta f1. Similarly, considering the second point of contact here, this is the normal reaction whose magnitude is equal to delta n2. And similarly, the friction force delta f2 will be in this direction, and it will have some different magnitude. Okay, let's consider the nth point of contact. The normal reaction at the nth point of contact will be delta n. Okay, and we will also have some different kind of friction force. And similarly, their resultants, okay, the resultant made by the normal reaction and the friction force will be delta r1 in this case, delta r2 in this case, and delta r3 in this case. So what we want to infer from this is that the normal reaction is not a uniformly distributed. Okay, the normal reactions are not uniformly distributed. Normal reactions in actual are different at different points of contact. So hence we won't get a uniformly distributed load as which was shown in the first slide. Okay, we won't get this kind of loading but we will get this kind of loading, which is somewhat a varying load. Okay, it can be uniformly varying load or it can be non-uniformly varying load, but it will be definitely a varying load where the magnitude of the normal reactions at different points of contact isn't same. Okay, it will be different at different points. Hence, we get a uniformly varying load. Therefore, the location of the centroid, okay, sorry, the location of the centroid of this varying load won't be at the center of gravity. Okay, it won't be passing through the center of gravity. So it might lie somewhere to the right side of the weight or to the left hand side of the weight. Okay, so since these normal reactions are different at different points of contact, hence we get a varying load, and the resultant of these normal reactions won't pass through the center of gravity. It will be somewhere to the right or somewhere to the left. Okay, so usually if the force is acting in this direction, okay, see here, the force was acting in this direction here. So since it was acting in the positive x-axis, okay, this is the positive x-axis, so this load here little bit relieves the reaction. Okay, this just eases the contact between the ground and this block. Okay, so if the force is shown in this direction, usually the normal reaction, okay, to the left hand side of the weight force will be less. Okay, because this force tends to ease the contact between the ground and the block. Okay, so if this is the block and I'm applying the force in this direction, so if this would have been the weight, then I can expect my normal reaction to be somewhere from the left. Okay, so we can see here in this schematic here, the weight has been shown here, and this is the resultant of all these normal reactions. Okay, this is the resultant of all these normal reactions, and obviously it is not passing through the centroid, okay, or center of gravity, but it is either to the right or to the left of the center of gravity, and here in this case it is to the right of the center of gravity, and it does not share the same line as shared by the weight force. Okay, so also one can see that now there are two cases which we have to study. First is tipping and second is slipping. Okay, so first of all we'll move to the condition of slipping. Okay, so in slipping here, the contact between the ground and this the contact between the ground and the block is not lost by all the points of contact. Okay, but see here in this case of tipping, what happens, this is the case of tipping. Okay, see here, only one point will remain in contact with the ground. Okay, we can see that on the application of some force, this block is tipping. Instead of slipping, it is tipping. Okay, instead of slipping, it is tipping. Then only one point of contact, okay, one point will be in contact with the ground, and the normal reaction will be shown at that point of contact, because the contact between the block and the ground will be lost at all the other points except about the point of tipping. Okay, so this is actually the tipping. But if we are studying slipping, if we are studying slipping, there will be many points of contact with the ground. Ground and block. Okay, there will be many points of contact between the ground and block. But in the case of tipping, what happens here, if this is the weight, this is the applied force P, this normal reaction now will be shown at the tipping point. Okay, this is the tipping point because this force will cause the body to tip in this clockwise direction. Okay, so only one point will be left as the point of contact, and this will be the friction force. Okay, this will be the friction force. Now one more thing is that how can we determine whether this block is slipping? So for slipping, what should be the condition? For slipping, obviously the applied force should be greater than the maximum value of the friction. That is, P should be greater than mu Sn. Only then the block will slip. Okay, and if it is equal to mu Sn, then there will be an impending motion. That is, it will just start to slip. Okay. Also, the resultant of the normal reaction. Okay, I mean to say that the location of this normal reaction can also be found out. Okay, so it has been assumed that if it is lying at a distance of x from the weight force, then we can find the resultant of the we can find the location of the normal reaction. Okay, so if this is point O here, we can make the summation of the moments about point O to be 0. So summation of moments about the point O to be 0. Then we can say that the friction force and the normal reaction won't cause any moment about point O. The moment will be caused by weight, and that will be in the anti-clockwise direction. The moment arm will be at x. Okay, this P will cause a moment in the clockwise direction. Therefore, this will be a negative moment. The moment arm is h. So this will be equal to 0. From here, we can get the value of x, that will be equal to ph by w. Okay, so this can give us what? This can give us the location of the resultant. Okay, this can give us the location of the resultant of the normal reaction. That is, the net normal reaction will be acting at a distance of x from the weight. Okay, from the line of action of the weight. So from this equation, we can also see that as we go on increasing the load, or if we go on increasing the height, the x goes on increasing. Okay, from this it is clear that x increases by increasing of the p and the increasing of the height. Okay, by the increasing of this height, which is h, and it decreases, and also it increases by decreasing the weight. X also increases by decreasing, that is, weight has to go down. Okay, then this distance will go on increasing. So suppose x is here. Okay, x is here. Therefore, after, if this x goes on increasing, a point will come that x will be here. Okay, this is the maximum value of the x. Okay, in this case, this is the value of the x. So we can conclude that if x is less than a by 2, okay, either positive or negative. Okay, because x has been defined from this here, it can be either towards positive or negative. Okay, because the normal reaction can be either from the right hand side or it can lie from the left hand side. Okay, so we can say that if x is actually less than plus minus a by 2, body will slip. Okay, the body will slip. Okay, obviously, because the normal reaction will lie within the body. Okay, it won't be at the extreme contact. Okay, the normal reaction won't be at any extreme end if x is less than a plus minus a by 2. Okay, fine. So if x is less than plus minus a by 2, then body will slip. Okay, because there will be a normal reaction, and that normal reaction will be within the range of a by 2, and if x is equal to a by 2, the body will, this will be the case when the body is tipping. Okay, because normal reaction is lying on the extreme end. Okay, the maximum value of the x can be a by 2. If it is lying on the extreme end, then we can say that the normal reaction is at the extreme end, which means that all the other points have lost contact with the ground, and this is the case of the tipping. Okay, so this equation helps us to determine whether the body is tipping or slipping. Okay, fine. Now, based on the discussion of the tipping and slipping, let's see one problem. Okay, one simple problem. Determine the maximum force that can be applied without causing movement of the 250-pound crate that is the center of gravity at G. The coefficient of friction is being given between the ground, the floor and the block. That is equal to 0.4, okay, coefficient of the static friction. So see here, it is saying that what is the maximum force without causing any moment, okay? So the moment here is, there can be two moments. See here, actually in this question, the dimensions of the block are being given. If there wouldn't have been any kind of dimensions given, we could have just checked the condition of slipping only, because without the dimensions we can't check the condition of the tipping. Okay, since here both the dimensions are being given, therefore we have to see both the conditions. Okay, first of all we have to check the condition of tipping or slipping, whatever. One condition of the slipping has to be checked and another condition of the tipping has to be checked. Okay, so we have to check both these conditions. Okay, and we have to find the maximum force without causing any movement. And sometimes this could have been asked that what is the minimum force to cause any movement. Okay, so maximum force without causing any movement, the same question could have been asked that determine the minimum force to cause a movement. Okay, we have to see, but in this case we have to check for two movements. One will be the slipping and another will be the case of tipping. Okay, so both the cases will have different free body diagrams because the normal reaction will be, the location of the normal reaction will be different for the cases of slipping and tipping. So first of all, let's see the condition case of slipping. Let's see its free body diagram. So this is the force F or force P here in this question. This is the force P. For checking of the slipping, let's assume that normal reaction is at some distance x. Okay, so for the case of slipping, the normal reaction should be within the range of 1.5 feet because this distance has been given as 1.5 and this distance is also 1.5. This height has been given as 4.5. This distance was given as 2.5. This is the center of gravity and this will be the weight, and this distance has been given as 3.5, and this will be the friction. Okay, this will be the static friction because we are checking for the impending condition. Okay, we are checking for the impending condition. So let's see what is the force required to cause slipping. First of all, we will see what will be the force that will cause the slipping of this block. Okay, the minimum force which is required to cause the slipping of this block. Since it is talking about the minimum force or the minimum force to cause the slipping or maximum force to avoid slipping, that is, we have to check for the impending condition. We're going to check for the impending condition. Let's apply the equilibrium conditions. So first equilibrium equation is that summation of the forces in the x direction should be 0. So the forces in the x direction is this applied force P, and we have a friction force in the negative x direction, so it will be negative, so this will be equal to 0. So applied force should be equal to F. And now since we are calculating it for the impending condition, therefore this F should be equal to mu Sn. Okay, it should be equal to mu Sn. And from summation of the forces in the y direction, we can see that this has to be 0. And from there, we can get that normal reaction minus W. It should be equal to 0. That is, normal reaction should be equal to W, which is equal to 250 pounds. Okay, I think it is given as 250 pounds. Okay, yes, 250 pounds. So from here, we can say that P will be equal to mu S. Okay, mu S, I think it was given as 0.4. It is equal to 0.4 multiplied by this 250 Newton, this 250 pound force. Okay, so from here, we can see that P is equal to, it comes out to be 100 pounds. So this is actually the force which is required for the slipping of this block. Okay, unless and until we don't apply this much amount of force, the slipping won't be possible. Okay, but we have to check that whether this block will tip before slipping. Okay, it is a possibility that at this force the block, okay, either at the force less than this p, that is 100 pounds, or greater than this 100 pounds, the block can tip. Okay, therefore we have to check for the tipping condition as well. So in this question, if the dimensions were not given, then we could have checked only for the slipping. Okay, because we couldn't have used the moment equation, but here we can use the moment equation to check for the tipping of the block. So the FBT for the tipping case will change, because the normal reaction now will be at the extreme end. Okay, it will, this will be the tipping point. Okay, let's say that this is the tipping point A. So again we can see that this is the applied force, and this distance was 1.5, this was 1.5, this was 2.5, this was the weight which was equal to 250 pounds, this is 3.5, this is the friction force, and this distance was 4.5, and this will be the normal reaction. If we apply the summation of the forces in the x direction, that has to be 0. P minus friction force, that will be 0. P will be equal to the friction force, but here this friction force is not equal to mu Sn, because this is the condition of the slipping. Okay, it is not equal to mu Sn, because we are checking for the tipping. Okay, only when friction force, only when we have to check the condition of slipping, only then we can say that friction force is equal to mu Sn. Okay, so here we can't say that friction force is equal to mu Sn. Now summation of the forces in the y direction should be equal to 0. It will yield that normal reaction is equal to the weight, that is it is equal to 250 pounds. These two equations aren't of the use, but here the equation which is useful in determining the value of the p, that will just cause the tipping of this block, that will be the moment equation. We can take the moment about the tipping point to be 0. Summation of the moments about the tipping point is equal to 0. Okay, why I'm taking, because the friction force and the normal reaction are passing along this, about this point, so they won't create any moment. Okay, they won't create any moment, so it will be easier to calculate. Now see here, again I am taking this to be 0 because it is the case, a limiting case. Okay, it is the limiting case. Okay, from this equation I will get that what is the force just required to cause the tipping about A. So see here, the moment due to will be due to now, due to this applied force W and applied force P and this weight W. So P will create a clockwise moment about A. Let's take it to be negative. The force arm is equal to 4.5. W will create an anti-clockwise moment about A. Let's take to be positive. And the force arm for it is this much, that is 1.5. So this has to be 0. From here we get that P will be equal to weight, that is equal to 250 pounds. And when we calculate this value, it comes out to be 83.33. Okay, it comes out to be 83.33 pounds. Okay, obviously it is less than, this is less than 100. 100 was what force required for slipping. Therefore, the body will tip first, okay, before slipping. The block will tip before slipping. So if the force on the block was 50 pounds, then nothing would have happened to the block. 60 pounds, nothing would have happened. 80 pounds, nothing would have happened to the block. But as soon as the value of the force 83.33, okay, still nothing will happen to the block, but just above, if we go above this force, the block will start to tip. Okay, the block will start to tip. So the force required for causing the slipping was 100. Okay, but before it is slipping, the body will tip. Okay, the body will tip because it is the minimum among them is this 83.33 pounds. Okay, so body will tip before slipping. Okay, and this could have been found here as well. Okay, we could have seen if we would have like to, अगर हमें ये calculate करते हम x distance. Okay, if we would have been calculating this x distance, so suppose this is the point O. If this is the point O, if I take the summation of the moments about point O to be 0, okay, we can see here the normal direction and the friction force won't cause any movement. P into 4.5, that will be in the anti-clockwise direction, plus the weight will, sorry, the P into 4.5, it will create a moment about O in the clockwise direction. Weight will create a moment in the anti-clockwise direction, whose force arm is equal to x. So this has to be equal to 0. Now see here, this value is equal to 100 into 4.5. That will be equal to weight into x. I think weight was equal to 250. 250 into x. So from here we can see that x is equal to 450 by 250. That is equal to 9.5, 9 by 5, and that is equal to 1.8 meters. So x here is equal to 1.8 meters, and this 1.8 is greater than 1.5. Okay, for the condition of the slipping. Okay, if the body would have slipped, then this x should have been less than 1.5. Okay, this was the condition of the slipping. So it is obvious from this equation as well, since x is 1.8 meters, therefore the body will slip before, sorry, the body will tip before slipping. Okay, if x would have been within this range of 1.5, then it would have slipped. Okay, and obviously the force would have been less than that of the tipping force. Okay, but this is not the case here. There is another question. The uniform crate shown in the figure. Okay, the uniform crate shown in the figure has a mass of 250 kg. Sorry, the uniform crate shown in the figure has a mass of 20 kg. If a force P is applied here, the force is given, okay, to the crate to determine if it remains in equilibrium or not. Okay, the coefficient of static friction is given as 0.3. So here in this question, the force has been given. We have to see whether this is in equilibrium or not. Okay, so let's see how we proceed for this question. So first of all, again, we have to check for the two conditions. Okay, the condition is that for the equilibrium will be the body should neither slip nor tip. Okay, neither slip nor tip, because the dimensions are given. We have to check for the both the cases. Okay, and since it's the uniform crate, therefore its center of gravity will be at the geometric center. This will be the center of gravity. Now we can draw the free body diagram of it. This is the FBT of the complete crate. Okay, complete FBT of the crate. This is the weight which is acting at the center of gravity. Okay, this distance will obviously be 0.4 and this distance will be 0.4. Now this is the applied force of 80 newtons, and it has been resolved into two components. So this will be, since this angle is equal to 30 degree, this angle will also be equal to 30 degree. Therefore, this will be 80 cos 30, that is 80 root 3 by 2, that will be equal to 40 root 3. And this component will be equal to 80 sine 30, that is 80 by 2, it will be equal to 40 Newton. Okay. The weight, another force that is here is the weight of this block, that will be equal to mg, and mass here is given as 20. Therefore, this will be equal to 20 into 9.81. Let's assume that this is the value of the normal reaction, and it is assumed that it is acting at some distance x from the line of action of the weight. Another force that will be here will be the friction force. Now see here, I'm not writing this friction force equal to mu n, because I don't know What is the state of this block? I can write friction force is equal to mu n only at the impending condition, but nowhere it is mentioned that the body is in the impending condition. Therefore, I'm actually trying to see what is the state of the block. Therefore, I can't say that friction force is equal to mu n. Therefore, I will simply write it by a variable that is known as this force F, okay, friction force represented by small f. So if I take the summation of the forces to be 0 in the x direction, we can see that in the x direction there is a force of 40 root 3 Newton in the positive x-axis, and along the negative x-axis there is a friction force that is equal to minus F. So this summation has to be equal to 0. From here we get that friction force has to be equal to 40 root 3. Okay, and if we perform the multiplication, it will be equal to 69.28. This friction force comes out to be 69.28. So we have currently assumed this to be in the equilibrium, and if we assume that this body is in equilibrium, we can use the equilibrium equation in the x direction, and we got the value of the friction force to be equal to 69.28 newtons. Okay, now let us use the equilibrium equation in the y direction. We can see that summation of the forces in the y direction, the forces in the y direction are in the upward direction we have normal reaction, in the downward direction we have weight, and there is another force which is the component of this, okay, the vertical component of this 80 Newton, that is 40 Newton in the downward direction. So this has to be equal to 0. We can see that the normal reaction here will be equal to 40 plus weight. The weight is equal to 20 into 9.81. We get that the value of the normal reaction, it comes out to be, after solving this, it comes out to be 236.2 newtons. Okay, this is the normal reaction. Now, if I want to calculate the limiting friction, okay, value of the limiting friction, limiting friction, that is F is equal to mu s times the normal reaction. Here the coefficient of friction between the block and the surface has been given as 0.3. So 0.3 multiplied by this normal reaction, that is equal to 236.2. And this limiting force of friction comes out to be, after multiplication, it comes out to be 70.86 Newton. Now see here, the force of friction which I obtained by this equilibrium equation is less than this limiting value. So what can we conclude? We can conclude that the body won't slip. Okay, I can write it in the next slide. Since force of friction, that is F equal to, it was equal to 69.28, is less than the limiting value of friction. The limiting value of the friction is equal to 70.86. This thing implies that the body won't slip. Now, how can we check whether the body isn't tipping or not? Okay, whether the body is tipping or not, that can be checked by finding the value of x. Okay, if x is within the range of 0.4, then we can conclude that the body isn't tipping. Okay, so for that, let's take the moments about, if this is the point A, let's see, let's take the moments about point A to be 0. Summation of the moments about point A has to be 0. Okay, if we are going to check for the tipping, then we can see that moment about A, that will be caused by this 40 root 3 force. Okay, moment about A will be caused by this 40 root 3 force. Another moment will be due to this 40 Newton force, and another moment will be due to this weight. Okay, another moment will be due to this weight. Now we can see that this is 0.2, this distance is 0.4. Okay, so we can see from here that 40 root 3 will cause a clockwise movement about A, and the magnitude will be equal to, taking clockwise movements to be negative, 40 root 3. The force arm for this force is equal to 0.2. Another movement will be caused by this 40 Newton force. Again, it will cause an anti-clockwise movement about A. Okay, sorry, 40 root 3 was causing a clockwise movement about A. This 40 Newton will cause an anti-clockwise movement about A, whose magnitude is equal to 40 into the force arm is 0.4 plus x. Okay, this distance is again 0.4 plus x. So this anti-clockwise movement has to be positive. This will be 40 into 0.4 plus x. We can see that weight is causing again an anti-clockwise movement. Okay, weight is causing an anti-clockwise movement. Then the moment due to this weight will also be positive, and its force arm will be equal to, we can see that it is acting at a distance of x from A. So this has to be 0. So from here, after making this simplification, what we get here is, we can see that this will be equal to minus 13.85. This will be equal to 16x. 40 into 0.4, that will be equal to 16, plus 40 into x, that will be 40x. And weight was 20 into 9.81, that is 196.2 x. So this has to be 0. So from here, after simplifying, the value of x comes out to be minus 0.009 meters. Okay, what does this mean? This means that since it came out to be negative, it means that normal reaction won't be here, it will be towards the left of side of the weight. Okay, the normal reaction in actual should be from the left hand side of the weight. Okay, so obviously we had a vertical component as well. Okay, hadn't this vertical component of the force being present, only if there was a horizontal force, then definitely the x would have been towards the, that is the location of the normal reaction would have been towards the right of the weight. Okay, but this vertical component a little bit tries to negate the effect, therefore it is from the left hand side. Okay, so what actually this specifies that normal reaction is from LHS of the weight. But it is within the reach of, this is within the reach of 0.4 meters. Okay, because our x value should be less or equal, less than 0.4 for the case of slipping. Okay, it should not be equal to 0.4 or greater than 0.4, otherwise the body will tip. Okay, so x value should be, okay, for sliding, x value should be less or equal to plus minus 0.4. Okay, and our x value is less than 0.4, therefore the body won't tip. Okay, the body won't tip. This means that this gives us the indication that body won't tip. Now in this problem, the body is neither sliding nor tipping, but it is close to sliding. You can see that the value of the friction force, okay, the limiting condition is that friction force should be equal to 70.86. Okay, friction force is equal to 70.86. The limiting friction, okay, it is 70.86, but our friction force is equal to 69.28, but it is very close to sliding. Okay, it is close to sliding. Neither it is sliding, it is close to sliding, but it is not sliding. Also, it is not tipping, because our value of x came out to be within the range of plus minus 0.4. Therefore, it means that the body isn't tipping. Okay, obviously there will be some greater force required for the body to tip. Okay, so 80, this applied force of 80 newtons here in this case isn't enough for causing the tipping or causing this what we call as the sliding of the body. Okay, hope it is clear.